Okay. All right. Great. Okay. Thanks. So, in starting, I have the pleasure of moving a little bit to the east, and we're going to talk about similar sort of sediments preserved in the bottom of Lake Crescent, the next big national park lake in Olympic National Park to the east of Ozette Lake. And I just want to, because I'll forget at the end, I just want to say that I'm presenting on behalf of my colleagues here at NC State University, but this has been a team effort with folks from the Continental Scientific Drilling Facility at University of Minnesota, the National Earthquake Hazard Reduction Program, part of the USGS, and then Danny Brothers and colleagues at the Pacific Coastal Marine Science Center, USGS, as well as Pat Pringle, formerly at Centralia College, who's always up for dating landslides in lakes, especially with tree rings. So let's go on to the next slide. And just like Lonnie, I have a bit of a story. We're in Raleigh, North Carolina today, but I grew up right on the edge of Olympic National Park at Heart of the Hills, for folks that are familiar with that, up just on the way up to Hurricane Ridge, and right along just next to the fault, which we now know as the Lake Creek Boundary Creek Fault, which is going to play a story underneath and in the sediments of Lake Crescent. So we're going to move to the east from Ozette Lake to Lake Crescent. And again, the same scenario plays out. There's the Cascadia subduction zone and its ability to generate large earthquakes in the region. But we're a little bit further east. And so we think that this part of the North Olympic Peninsula, and certainly as you move closer to Puget Lowlands, experiences also earthquakes from shallow crustal faults. So let's look at the next slide. These are two shake map sort of modeled scenarios for the perceived or potential shaking intensity from, on the left, a Cascadia subduction zone magnitude 9 earthquake. This is a model of how intense the shaking would be across western Washington. The blue star would represent Lake Crescent. And then on the right is a 2006 model of a local rupture on a fault that's just south of Port Angeles, the Lake Creek Boundary Creek Fault. And I think if you push the button, there's a little pop-up that should come. Just advance the slide one. Yeah. And we now know since 2006 that this fault, the Lake Creek Boundary Fault System, or what's known as the North Olympic Fault Zone, extends not only to Lake Crescent, but underneath Lake Crescent and then further to the west. And so if we include the full rupture length, we might expect a magnitude 7 to 7.5 earthquake in the North Olympic Peninsula region. So okay, next slide, please. So one of our goals here at Lake Crescent is to look at, are we in a location such that we can record the sedimentological evidence for earthquakes happening, both number one on the Cascadia subduction zone, and then number two on these local crustal faults. How many of these do we record in the last maybe 10,000 years or so? And what are their impacts relative impacts on this lake, which can then maybe tell us about the intensity of shaking that we would experience in this part of the Olympic Peninsula. Next slide, please. Okay, so as hopefully everyone's been to Lake Crescent. If not, put it on your bucket list of places to go, along with Ozette Lake. They're both amazing. One of the things that is so fun about this work is you get to go and spend time in some of the true gems of the national park system and conduct hopefully meaningful scientific research. And it's just been such a pleasure to be able to do this in such a beautiful environment. So Lake Crescent, it occupies portions of two parallel valleys. These two valleys are fault controlled. So there's faults that control the valleys, the topography of the valleys, and the valleys were over deepened by glacial scour about 15,000 years ago when the Cordilleran ice sheet advanced into the northern part of the Olympic Peninsula. They have really steep hill slopes, both the subaerial hill slopes as well as underneath the water. The hill slopes that we can't see on the lake margins are very steep. There's over 1 kilometer of vertical relief between Pyramid Mountain, which is the peak shown there in the photo, or where I'm standing in this photograph on top of Mount Storm King. There's not that much fluvial delivery into the lake. There's only one perennial stream, which is Barnes Creek. And you can see the delta of Barnes Creek in the lower center part of the photo. And importantly for Lake Crescent, there's a cool sort of fish biology story in that there's several endemic species of trout that have been recognized in Lake Crescent. And I'll come back to that at the end. Next slide, please. Okay, so our hypothesis is that the sediments at the bottom of Lake Crescent, they're going to preserve evidence for Holocene earthquakes, and that they're going to preserve evidence for earthquakes on both the North Olympic Fault Zone, these local close by, in some cases the fault is rupturing right underneath the lake, and they'll also preserve evidence for the bit more distal but maybe larger Cascadia subduction zone events. This image here is just showing the data that was collected by Dr. Brothers and colleagues with the USGS, where they have chirp seismic data collected over in Lake Crescent in 2019. That's overlain on the bathymetry that we collected with other collaborators from the USGS at Pacific Science Center in 2017. And so we can get this really cool view of the lake floor topography, and we can see big landslide deposits in the lake floor. And then with the 2019 chirp data, we can see into the subsurface, just like Danny presented for Lake Ozette to the west. Okay, next slide, please. Okay, so we just right up front, because time is limited, we recognize two types of event layers in the stratigraphy formed by earthquakes. One of these are earthquakes that are the big event layer one would record what we believe are earthquakes on the North Olympic Fault Zone. So these are local earthquakes close to Lake Crescent. And they also seem to be accompanied by large subaerial rock slides that are coming down into the lake. And those rock slides, some of them are millions of cubic meters. We can see those deposits on the floor of the lake today. Those rock slides we envision are generating big displacement waves, or tsunamis within the lake, to then help to mobilize sediment along the shorelines of the lake and account for some of the really thick, the great thickness of these deposits. The second type of event layer are the turbidites that were just discussed by Dr. Brothers and Dr. Leithold over in Ozette Lake. These centimeter to decimeter thick turbidites that are forming due to failure of the margins of the lake, underwater margins of the lake, and transport of sediments from the lake margins down into the deeper basins. Okay, next slide, please. Can folks still hear me? Can we advance to the next slide?
There's sometimes a lag.
Okay, all right, sorry, Hayes. I'll just wait. Okay, here, yeah, great. Okay, so so there's three main depositional basins in the lake. One to the north with the letter the letter N. One in the south central part, the South Basin, and then one to the southwest. We're going to focus most of our discussion in the Southern Basin, where the two red dots are. That's where we retrieved our most recent sediment cores in the lake in 2020. Next slide, please. Okay, and just like with the USGS folks, we used what's known as a UETech sediment coring platform. This one is operated by the Continental Scientific Drilling Facility at the University of Montana. At the photo here in the Southern Basin, the coring platform sitting over 184 meters of water. So the bottom of the lake here is below sea level. From this location, we recovered in total about 60 meters of core. Two of those cores were about 24 meters long. And we, just like at Ozette Lake, we recovered the Mazama ash in our cores about 15 meters below the bottom of the lake bed. And our core base, we bottom out at about 10.2 thousand years old. So maybe not quite as old as that Ozette Lake. Next photo, please. I put this in here just for folks. We've been coring in Lake Crescent since 2015. We've had 3 coring campaigns, 2015, 18, and 2022. And much of the core material is archived at the Continental Scientific Drilling Facility campus at the University of Minnesota. And those are archival cores that are available for folks if they're interested in working with the sediments in Lake Crescent. Next slide, please. Okay, here's what the seismic data looks like. And what I want to highlight are these lighter colored packages. There's 4 of them: mass transport deposit 1, MTD 1 through 4. We recognize 4 of them in this sediments of Lake Crescent. And I've just, in the interest of time, put the ages on there. So about 3,000, 4,000, 7,000, and 7.2 thousand years ago, kind of on average, would be the ages of those. Again, these are ones that we believe formed by earthquakes on local faults. Next, we're going to zoom in on that blue box there, and we just look at the upper section. In this upper section, we have between the green lines, the mass transport deposit. We see a chaotic lower unit that we interpret as being mass wasting or landslide debris into the bottom of the lake. It's overlain by these lighter colored transparent upper units, which represent the rapid sedimentation of material into the lake. And then that's overlain by background or kind of the regular sediments in the lake since the most recent mass transport deposit occurred about 3,000 years ago. That upper seismic facies, SF1, is the one that contains the turbidites associated with the Cascadia subduction zone earthquake events. Let's go forward to the next slide. So, Dr. Brothers talked about criteria that we could use to see whether or not these event layers are triggered by earthquakes. And one of the ones that we used here at Lake Crescent, as I'm sure they did at OZ, was looking for transport directions and thicknesses of these deposits. So these are isopack or thickness maps of the different depositional basins for the uppermost mass transport deposit, showing that sediments are coming into the basin from multiple different directions. And that's one hallmark of an earthquake trigger as opposed to, say, a flood trigger. Next slide. This is sort of another way to see that. So that last image was showing you the mass transport deposit thickness variations. This is showing us turbidites from above Cascadia subduction zone. And what we can see is that there are each color represents a different turbidite, and we can see that they're sourced from multiple different locations. Thus, we think they're occurring during earthquakes. And I'm getting the stop sign. Can I show just one more slide, please, for concluding? Okay.
Yes, go ahead.
Okay, so let's go forward one more. Okay, so here's our record for Lake Crescent. In green are the turbidites that we believe are triggered by the Cascadia subduction zone earthquake. In blue, there's a thin blue line, that's the Mazama tephra. Most of our turbidites are above the Mazama tephra. We have 20 of those in Lake Crescent, and the gray bars are the earthquakes and their deposits, the deposits from earthquakes that are triggered on the local North Olympic Fault Zone faults. So in total, 24 event layers in Lake Crescent since 8.1 thousand years, likely all earthquake triggered. And that would give us an overall recurrence interval about 1 every 340 years, an earthquake recorded in the sediments, on average about 1 every 340 years since in the last 8,000 years for Lake Crescent. And I'll leave it at that.
Right, excellent. Thank you, Carl. Any questions for Carl? Don't see anything in the chat yet, except a comment about, did you run away before the next Cascade subduction zone earthquake? That's a funny one. Heather asks, in your isopack maps, did you use the cores to get your thickness values and then interpolate them between the sampling points?
We would have used the cores to validate, but the thickness values are coming from the CHIRP seismic data and mapping the thicknesses in those overlapping seismic lines. So that data is mostly coming from the isopack maps are mostly derived from the seismic data, and then our cores are only in a few places. We corroborate where we have the cores.
All right. Any other questions for Carl? Harold Tobin asks, the youngest MTD is about 3,000 years, but recurrence intervals prior to that is about 1,000 years, approximately. Any thoughts on the environmental change adding to deposits less likely versus a real gap since 3,000?
Well, okay, so what I guess one thing we can say is what we know from there's been a fair amount of subaerial trenching done on the Lake Creek, Boundary Creek, and the Sadie Creek faults. And there's pretty good evidence that there's an event at about 1,300 years before present. We see a small turbidite in the lake at 1,300 years ago that doesn't seem to correlate with the Cascadia subduction zone event that may be triggered on a portion of the North Olympic Fault Zone that didn't rupture underneath Lake Crescent. So maybe I'll leave it at that for right now. But I guess it does seem that the four big mass transport deposits seem to be relatively close in time with gaps between when they occur.